It is a statement of fact for me that test-driven development improves the quality of my code. I believe that this is true for you too, and for all software developers. Unlike most techniques and most processes, test-driven development amplifies the talents of the software developers that adopt it. So what do I mean by all of that, and how can I demonstrate it? Let's take a look. Hi, I'm Dave Farley of Continuous Delivery. Welcome to my channel. If you haven't been here before, please do hit subscribe. And if you enjoy the content today, hit like as well. I'd like to begin by thanking our sponsors, Equal Experts, Octopus and SpecFlow. They all have been supporting this channel for a long time, so please do support them in turn by checking out their links in the description below. Test-driven development allows you to learn from your code before it's too late. Knowing how to learn from your code enhances your ability to deliver world-class quality code at speed. This is the kind of modern software engineering skill that organizations dream of having in their development teams, opening up more lucrative options for developers. If you're interested in learning more about test-driven development, my brand new training course, Test-Driven Development and Behavior-Driven Development Designed Through Testing, is available now. Check the links out in the description below. Test-driven development is not the same thing as unit testing. TDD is explicitly about driving the design of our code from tests. Practitioners, me included, say that it's much more about design than it is about testing. In fact, in the early days, I remember people debating if it should be described as test-driven design rather than test-driven development. What this means in practice is that we start with a test and use the test to design the external view of our code. We do this in a series of simple steps. Red, write a test, run it and see it fail. Green, write some simple code to make the test pass, run it and then see the test pass. And refactor, make the code and tests cleaner, more expressive, more generic and better designed. At each stage, we should be thinking about different things. Writing the test is probably the point at which we should be thinking hardest. This is us thinking about the design of our code from the outside. We're consciously putting ourselves in the position of somebody using our code rather than somebody producing it, because we want to use it to write this test. Since we don't actually have the code yet, what we're really doing is designing how we expect people to use our code. We'd have to be idiots to make our own lives more difficult at this point by making it hard to write our test. So instead, we'll try our best to design our code to be easy to test and so easy to use. If at this point your test is difficult to write, then think again about how you could change the design of your code to make it easier. That's the real game here. This is the vital step that people that write tests after the code is done often miss. This is where nearly all of the value of test-driven development comes from. Having the tests is nice, sure, but that's not the real goal of test-driven development. The real goal is well-designed code. The first step in writing your test is to think about what it is that you want from your code. This seems to be a stumbling block for lots of people. Some people seem to be unable to think of their system without thinking of the solution, the code itself. But think about that for just a second. How can you come up with a solution if you don't understand the problem? You can't. It's not enough, it's not much help for me to answer 42 if we don't say what the question was. So either you're fooling yourself into thinking that you don't understand the problem, or you really don't understand the problem, in which case you're not ready to write any code yet, with or without tests. To be fair, it's sometimes difficult to figure out what test you want to write next, but what you are facing here is not a problem with testing, it's a problem of understanding what the next step should be in solving the problem. Part of the trick to test-driven development is to work incrementally in very small steps. I think this is the real challenge for people not used to test-driven development. It's not the testing, it's this incremental approach to design. There's a degree to which test-driven development strongly encourages us to make progress in smaller steps, and this is a very good thing. But it can be a bit of a culture shock if you aren't used to working that way. The trick, I think, is to go with the flow. Be guided by the test-driven development approach. Good tests in TDD express expected outcomes, never specific solutions. If you can't imagine throwing away your code and replacing it with an alternative implementation, then your tests aren't very good. We want tests that say what the code does without saying how it does it. Here are a few tests. Can you see what the code does? Can you see how I implemented it? I think that the answer to the first question is yes, and to the second, no. Just to demonstrate my point, here are two different solutions that both make all of these tests pass. This is important. It means that these tests provide protection, the kind of protection that TDD promised us in the first place. But many people who misread TDD as simply meaning unit testing failed to see. If you write tests after you wrote the code, you tend to only test that the code that you wrote is the code that you wrote, rather than testing that your goals that you set for your code were met. Plus, there's no pressure from tests that come later to make your code testable. And the testability of your code is a fantastic tool to use to steer the design. Let's take a look at that in a bit more detail. Here is some code. This code takes a word as input. It then reads in a list of words and looks for anagrams of the input in the list. Finally, it prints out how many anagrams it found and lists them all. I wouldn't usually write code that looks like this. It breaks too many of my own coding guidelines, but I see code that looks like this all the time, so I don't think it's some grotesque, unrealistic caricature. I think that this is representative of the kind of code that we all see. In my modern software engineering book, I list 5 qualities of code that allow us to manage complexity. I recommend that you use these 5 qualities as hallmarks of good design and consciously steer the design of your code to enhance them. Well-designed code is easy to change because it's modular, cohesive, has a good separation of concerns, it uses abstraction to hide information, and is coupled appropriately with a preference towards looser coupling. This code is clearly not modular. Everything is together in one place. You could argue that it's cohesive because everything is close together, but I think that's a rather naive view of cohesion. In cohesive code, everything that we see is related in some way. This code has a jumble of ideas, all in a single function. Which brings us on to separation of concerns, which is clearly terrible here. This code is doing at least 3 different things. It's reading words from a dictionary, it's looking for anagrams, and then it's printing out the anagrams that it finds. So it definitely scores 0 for separation of concerns. I could have actually made it worse. I could have inlined the isAnagram function, but I couldn't bring myself to that level of depravity, to be honest. Abstraction, well, there isn't any here, really. Essentially, the show anagrams function is saying go. It's about abstract in the same way that void star or object is abstract. It's too abstract to be really very helpful in us understanding what's going on. Finally, is this code loosely coupled? Well, obviously not. We have the location of a file hard-coded into the solution, and we have the code printing directly onto the console. All of this tied irrevocably to the finding of anagrams. I said earlier that the testability of our code was a good guide to high-quality design, so let's take a look at the tests for this code. Well, there isn't one really. I wrote this, which allowed me to run the code and look at the results. But how do I tell if it worked or not? Actually, I'm pretty sure that there is a bug in this. Can you spot it? If I wanted to test this, how could I? Well, I'd need to intercept attempts to write to the display somehow. so that I can see what's being displayed, because that's the only output from this code. That's possible, but it's not very easy or very pleasant. I could change the code to inject the print function, but now I'm just proving my own point that I am improving the design to make my code more testable. If I was being thorough, I will need to replace the dictionary of words that I used so that I can control the variables specifying targeted lists of words for my tests. I could do this for the code, but it would mean moving files around in this example. And these files are the files that my operating system uses as its dictionary for spell checking. So that sounds fairly unpleasant too. I hope that you will all agree that as it stands, this code is essentially untestable. So let's now start from the other direction. Let's start with a test, and the best starting point is always the simplest case that you can think of. So the heart of this problem is finding anagrams. Let's begin by focusing only on that part of the problem. We'll worry about the other stuff later on. That doesn't mean that we're going to forget about it, but I'm going to begin with a design assumption, led by my rules for managing complexity. I want my design to exhibit a clean separation of concerns, and given this problem, my best guess right now is that there are 3 concerns. We need to provide a list of words from somewhere. We need to, given a new word, we need to find anagrams for it in that list, and then we need to display the results in some way. So we will assume these are 3 distinct parts of our code, and I will start with the anagram solving part, because that's the heart of the problem. The simplest example that I can think of for an anagram is that a word is an anagram of itself. So here's my first test, and look, I've already made some design decisions for my solution here. I've decided that I want a class into which I can inject a list of words. Immediately, even before I've written any real code, this design choice means that my code is now more modular and more loosely coupled. It also means that the separation of concerns is improved, because this code that I'm testing is only focused on one thing, finding an anagram. My next step is to do just enough work to make this code compile and run without any mistakes, but not yet so the test passes. I want to see the test fail. That allows me to check that the test works. Now I can add enough code to make this single test pass. I'd probably start with something like this, and then after refactoring maybe end up with something like this. It's in the refactoring step, not the green step, where we do proper implementation design, because that's when we've got a passing test which reassures us that the changes that we are making are working correctly. What's the next simple behaviour that our code will need to show if it's working properly? Maybe it should reject words that have additional letters in them because they're not true anagrams. We should certainly be able to find multiple anagrams if they're in the supplied word list. Look at how our design choice to separate the word list is starting to pay off now. It makes it really easy to focus our test on the things that matter to us in that single test case. We will iterate, adding tests to make us add behaviour. And finally, let's add a test to check out our ability to display the results. Here's the test. This test has taught us something new. I suggested at the beginning that we'd assume 3 separate concerns, display being one. But the test that I've written so far didn't include a display because they didn't need it. In this test we do. So now I can decide how I'd like my design to work. I can progress the design of my code at this point. I could choose to inject the display on every call to list anagrams, or I could do what I did here and add it at the point at which I create my anagram solver. Here's the code that I wrote to make all of these tests pass. If we're treating our tests as a design tool, we don't need to agonize over being exhaustive with our tests. Looking at this, there's an obvious test that I could have added. We should maybe think about rejecting words that aren't anagrams. I didn't think of that the first time around, but now I have. I could still add it and the test would pass, but I don't have to because I used a different test to test the same behavior. You don't have to be perfect in your choice of tests. You choose your tests to drive the design step by step. Let's look where we ended up. We have our 3 concerns. Maybe you're worried that I haven't finished. So here's the code that gives me the functional equivalence for the first horrible piece of code that I showed you. Clearly, my code is more modular. I have 4 pieces, 4 modules here, each dealing with a separate part of the problem. I could further abstract these pieces instead of assembling the pieces here. I could more clearly name my pieces like this. I could choose to make each of the parts completely separate, each in its own module. Each small piece of this code is now clearly focused on only one part of the problem. The code inside each piece is only related to that part, and all of the code is related to that part. So my code is considerably more cohesive than the design that I began with. There's one part of this design that I personally rather dislike, that doesn't separate concerns well enough for my taste. That's here, where we display the results. This code would be much nicer to my eyes if it didn't have the strings to be displayed in the same place as the anagram solving. That would improve its separation of concerns and enhance its flexibility. I left it like this because I wanted to make this point. You can stop wherever you want. If I don't care about, for example, internationalizing my code, then I could stop here. But if I do care, I probably want to drive that from a test. And that's going to allow me to check that my anagrams code doesn't care about the language that we are using. And that test will force me to separate this concern too. The abstraction in my code is considerably better than before. The anagram solver only cares about lists of words now, not files on a special place on my disk, and it's no longer directly coupled to the console either. I could pass any function that takes a string now, and it will be supplied with anagrams. So we have improved abstraction and reduced coupling in the same step. This is not just better tested code now. This is better designed code. As a result of these changes, this code is dramatically more flexible than before. I can find anagrams in any list of words, not just my dictionary. I could easily imagine writing code that pulled a list of words from the web. My anagram solver can work with that without any changes. I can print to the console as before by passing the print function for my display. But equally, I could write a display that rendered the results in a web page or hovering in 3D in virtual reality if I wanted, because the design is better. My code no longer cares. I could even change where the inputs came from, allowing you to type the entry into a console, or maybe interpreting the spoken word. Okay, I could have done that with the original version too, but you can't blame me for trying. These changes came not from me being some brilliant programmer, but simply from the act of writing the test first and trying to make that process easy. Test-driven development is the best talent amplifier that I know of. And it gives us the earliest indication of when our design is poor that I know how to get. If you find it hard to write a test, it's telling you that you need to do more work on your design. By following the simple mantra of red, green, refactor, our code is better. We learn faster. We make progress in more incremental, more controlled manner. Our tests are more decoupled from the code that they test, so they're more durable. Oh, and as a nice side effect, we end up with some handy unit tests too. Thank you very much for watching.